Awesome, thank you. Well, I'm an Aggie, and as Aggies do, you have to make it offensively known that you're an Aggie. So I'm going to start with a howdy. Howdy. Awesome. Well, thank you, Dan, for having me. I came out to one of these before and had a really good time, so it means a lot that you'd let me speak at one of these. But let's hop in here. I'm excited to present, if this clicker clicks, a long-named presentation. Unlocking series elastic actuation in harsh environments, backlash-free magnetic gearing. I thought that name sounded good in an email, then now saying it, I thought need a shorter version. So you also could call this presentation Robots in Space. Try to make it more accessible for everybody. Because we could talk about gears all day long. That's what Fluxworks does, is we make magnetic gearboxes and magnetically geared actuators for robotics, advanced manufacturing, aerospace, and defense industries. Rather than getting immediately into the weeds, Dan kind of gave the recommendation, why don't we look at a case study? And that's exactly what we're going to do to them, Aggies. We're going to jump into space humanoid robotics, a particular problem that they had for a future mission that we continue to work on with NASA and other stakeholders. It's pretty fun. And that's going to dive us into what are series elastic actuators, what are magnetic gears, what's kind of their history, and now what do we do as a company with magnetic gearing. So let's before we dive into that, let's talk about just a little bit of my background and why the heck am I talking about gears. So born and raised in Keller, Texas, Texan through and through. Moved to Houston last year, married to my smoking hot wife, Chloe. Aggie engineer, love Jesus. I founded and serve as the CEO of Fluxworks, and I've got some of my team here. We're a team of 8 up in Conroe, Texas, where we've got 9,000 square foot of manufacturing. And love gears, motors, play the drums, like to rock climb. I love meeting new people and going new places. So events like this really fill me up. It's pretty fun for me. Here's my smoking hot wife. I've got a cat named Maxwell's stress tensor. It's my favorite equation. And this picture of me rock climbing. So I'm going to ask, but the old guys in the room don't get to answer this. So actually, if someone that's like a current student could answer, can you name these robots, or even get a few of them? Space humanoid robots is not that radical of an idea. We've been thinking about this for a long time. It's been in sci-fi for a long time, but it, maybe at first thought it doesn't seem very practical. It's just a fun sci-fi thing. But in case you didn't know, robots are in space, actually. This is a picture from 2011 with Chris Cassidy, a Navy SEAL and astronaut, working hand in hand with Robonaut 2. It's got little Cole Morgan servos on it. Renishaw encoders. I mean, this is a commercial off-the-shelf, a bunch of components to create this Robonaut. So we're going to talk about why the hell would you put a robot in space, and what are some of the challenges that this robot had that's making it not take up as much. So we'll get into all the reasons why you might want a robot in space, but why did that one get shipped to the ISS? Why did Robonaut get there? Well, a lot of reasons that NASA was thinking about, but we'll take one use case in particular. Is a famous example from 2008 that really got people starting to think, holy cow, we need some full-time autonomous systems to support the maintenance and sustainment of these space mechanisms. So the exact situation, and I want to read it to get it right, was that there was a gearbox driving the solar arrays that had been unable to automatically point the right side solar array towards the sun and get maximum energy efficiency. NASA suspects particularly that the lack of lubrication and all the mechanical gear shavings in this giant gold gear on the Alpha solar array gimbals was the particular reason for this problem. It was plaguing the station for about a year. So the Endeavour mission had 4 spacewalks that were a part of it, where 2 astronauts on each of those spacewalks were actually going out, and they would climb a 80-foot tether to get to this particular gear, and they had a toolbox with them that had this grease gun, and they were going to replace the bearing and re-grease the gear. Does anyone know how much a spacewalk costs once you're already up there? It's about $15 million per astronaut. and they had to do 4 walks with 2 astronauts each. And pretty famously, the toolbox flew away from the astronaut. And so you can see a picture of it flying away there. And so it was 1.5. I rounded up. It's still exciting to know where your taxpayer dollars are going, right? Is this kind of clunky mission. And you can imagine how unsafe it is too to take on these systems. So the idea of that robot was that they wanted a robot that could autonomously live full-time outside the station and crawl around and do maintenance to replace all these spacewalks. So now that's the second generation of this robot here, called Robonaut. Some people, the second generation, they call it the Valkyrie robot now. And it got a lot of attention, especially in about 2015 is when this robot started getting a lot of attention. Here's a little video here from a recent conference that talks about one of the core innovations that makes this particular robot so special. So you can see it's working with a human here, and what's special about it is all the rotary actuator joints in this robot have a series spring with them in order to create a more compliant kind of gear mechanism. They're adding artificial compliance to it. And what you do when you add a spring in series to an actuator is you call it a series elastic actuator, and you put a strain gauge on it, and it creates unparalleled torque sensing. So that way you can actively control the torque to a T for these robotic mechanisms. There's modern demonstrations of robots being able to handle eggs that have series elastic actuators without damaging the egg. So it's kind of an interesting technology, right? That's been around, but it's really started to take off since this first robot. But you can see that this one still was a little bit clunky. There's sometimes people had to hand them tools and parts, etc. And here's just a breakaway of the old robot, and you can see it kind of unshirted, and you can see the hand there, and these are the custom springs that NASA had manufactured to put in series there with that robot. They had to use custom particular strings with certain thermal properties, so that way, as you know, sometimes the deflection of the spring changes with temperature, right? The coefficient of thermal expansion, and also change of material properties. So NASA needed a good grasp on it, but even still, it's pretty difficult as the temperature changes over just even terrestrial applications to have an accurate strain gauge on it. But I'm going to slow down to kind of start to get into the weeds of the technical here, but giving a high-level picture first was that robot that really started getting people excited about series elastic actuators. And if you want a picture of 2 types of series elastic actuators, there's a kind of a generalized circuit diagram of it, where you put some spring in series with the gear train and the motor. And here's a rotary to linear application where you would hypothetically put a manual spring here on kind of this rack and pinion setup. And again, the reason for doing that is so that way you can have precise torque sensing and actually create compliance to make your whole system modelable, controllable, observable. Really the people that really first put this in a paper and kind of the core innovators of this technology came out of MIT. There was a foundational paper that was published in 1995 just called Series Elastic Actuators that really derives why is this so cool for modern robotics from a controllability and observability perspective. So here's the commercial hand that is advertised as being able to handle eggs safely because it's so dexterous and has such precise torque feedback. So when asking who cares about series elastic actuation, is it just a NASA need? Well, no, it really started to take off in advanced manufacturing. You can imagine a handling of semiconductor wafers. It also started to take off in healthcare. Here's a pretty mature company that just raised $400 million, Harmony Biotics, that actually uses them for human collaboration for physical therapy applications. So that way humans can really safely and gently work with these very springy robots with very springy joints. One of the ideas that people are trying to really continue to push on this is y'all are roboticists in here, so you know that some cobots struggle with speed, right? And also some of these safety features that some of them offer, it's tough for these systems to move extremely quickly and still be human safe and have a quick shut-off break. There's videos of some of these early series elastic actuator robots of someone actually coming in contact with them and touching them with their hand as their robot is flying around as a pick and place, and actually it has an artificial back drivability. As you touch the robot, it just compliantly yields to the person touching it as opposed to the robot having to stop. So it's a really exciting idea that people are starting to think about. But let's really get into what was NASA's problem and where did magnetic gears come into place. So as you know, these precision mechanisms are going to use precision motors, precision gears, and because it's these series elastic actuator applications, you're going to add a spring and usually some sort of strain gauge, like a force torque sensor in there. Because these applications need to know position and torque in order to fully do impedance control. So the problem, as it might be obvious, is this is expensive. Putting this in like every single joint of some of these robots, like the Valkyrie robot, was millions of dollars to prototype, and even at commercial scale when you're buying all these sensors and precision machine gears and trying to be backlash free as much as possible, because that creates areas of uncontrollability, it can really start to add up. But now let's turn it on hard mode. So NASA, going back to the moon with the Artemis missions, is trying to target reaching areas where there is ice on the moon. The only place where ice can exist on the moon is permanently shadowed regions of the moon. These are regions that, since like God created the universe, or whoever you want to say created it, have such a big crater in them that for all of time, sunlight has never actually hit the bottom of that crater. So it is actually the coldest place in the known universe. There is no other naturally occurring place that is that cold, not even deep space, because it's still at some point you're getting starlight on you. And by how cold, we mean it could be as low as like 3 Kelvin. They're not sure. But the spec was written for 30 Kelvin. So you're getting pretty close to absolute zero. I think even electrons start to shiver at that sort of temperature. And here's the rest of the specs. So, the low temp and then the high temp, a pretty nice 400 degrees Celsius range, easy. Hard vacuum, and then going through launch, it has to deal with massive acceleration. These are tiny, precise little gears and actuators. And also radiation on the moon. Have you ever tried to measure something with a strain gauge over a 650 degree Fahrenheit range? You get quite a bit of thermal expansion, and even the strain gauge itself is expanding at that time, so your readings are way off. Also, because it's NASA and they like to write really aggressive specifications, they put out an RFP asking for not only robotic actuators that can handle these temperatures for their future Artemis missions, but also compared to the Apollo gear mechanisms, they wanted it to be 4,000% higher lifetime and 21 more points of efficiency, from 59% efficient to 80% efficient. Got the idea yet? This is one of arguably the hardest, environments almost imaginable. This is a pretty aggressive specification. Enter the idea magnetic gears. This is one of our first prototypes shown there on the side, transferring torque contact list there. They are naturally series elastic because the gear itself is springy, which we will get into in just a little bit. It is naturally backlash free. There is no teeth contact, so the flux sort of acts more like a rubber band as you move about the gear. It's highly back drivable. It is safe for you, the system and the gear itself, and by that I mean magnetic gears have an intrinsic clutching property. When you overload them, there is a designed-in torque that at that torque, the gear just clutches and it slips itself until you lower the torque and bring it back into place. So it is not possible to ratchet or strip a magnetic gear, which can be pretty attractive for applications where you might stumble into something or have a massive shock load that you don't expect, and you don't have to oversize your whole system for that. This is the only place that I saw that the font messed up, and we decided we were okay with it. So it just says cheat codes. With magnetic gears, you can get cheat codes. Magnetic gears, because they're a spring in nature, a geared spring, y'all know Hooke's law, right? how much you displace a spring, if you know the spring constant, you know how much force you get. Well, same thing with a torsional spring. If you know the torsion spring constant, you know how much you displace it, you know how much torque you get. So actually, just using the encoders or resolvers that are already on the actuator, we have proven that we can measure torque already within 1% accuracy compared to a calibrated Himmelstein precise torque sensor. Within 1%, and you dump the whole spring, you dump the whole torque force sensing component, and you can use the cheapest encoders that you want. You still get incredible resolution on your torque sensing. So that's what we mean when we say cheat code. That's kind of one of the exciting things about magnetic gears, right? So who first thought of magnetic gears? Well, I did not. I wish I could claim that, but actually the earliest patents go back to like 1901. It's not a crazy idea, right? You just take, instead of teeth that are meshing, what if you just put magnets, right? But these early topologies really didn't take off for two main reasons. One, poor magnet utilization. As you can see, all these, oh, I've got a laser, right? Oh yeah. As you can see, you're only getting like torque transfer in some of these topologies with one magnet to one magnet. You can imagine compared to a mechanical tooth, you're going to need way more magnet and a lot bigger gears in order to get the same torque and power out of that system. So these early topologies were really unimpressive. Additionally, magnet materials used to suck. There's been a lot of advancements, especially in the past 30-ish years, that make neodymium magnets more commercially available. And so neodymium magnets are the closest thing we have to room temperature superconductors, and they're pretty powerful magnets. About 30-ish years ago, and actually I was looking it back up again, I saw it was 2001, so I was wrong, it was like about 24 years ago. Some chap from the UK named Kaisa Tulla patented this type of gear. We're going to spend just a little bit of time, but not a lot of time, talking about how it works, because I want to talk about our gear and how we solve this NASA problem. But the basic idea that he came up with got people re-excited about magnetic gears. The idea was, what if you make it a lot more like a planetary gear? You have three bodies, the sun, the planets, and the ring, and what you do is you fix one of the rotors, just like you do in a planetary gear, and you can get a gear ratio, but the way that you're actually getting the speeds to match, right? Because north magnets and south magnets, they want to couple directly to each other. How do you get these two magnets to move at different speeds, and how do you get two rotors with a different number of poles on them to couple with one another? Well, what you do is you modulate the flux. And it's actually called a flux modulator, is the original patent, and it's pretty cool because it sounds like flux capacitor. So we're getting pretty close to like some pretty crazy sci-fi stuff, right? But what you're doing, and I like to compare it to like electricity. I think, it's not magic. Maybe that's an electrical engineer. But like, you can think of it as there's places where the flux wants to go, and there's places where the flux doesn't want to go, just like an insulator or a conductor. So these little steel pieces in the middle are the secret ingredient for the Kaisa Tulla coaxial magnetic gear. What it does is the flux wants to pass through those steel pieces, but it doesn't want to pass through air. So what you're doing is you're taking a square wave and you're modulating it with another square wave in order to create a new frequency. Has anybody done Fourier analysis? Any of my engineers here taking like Cal 5 doing Fourier decomp? I'll show you the derivation sometime. It's pretty sick. So the basic idea is if you don't fix one of the rotors, the way that this one works is it's got this steady state speed equation. And as long as this law is true, where the number of modulators equals the number of pole pairs on the inner rotor plus the number of pole pairs on the outer rotor, then you get this equation, which is relating all the mechanical speeds of each of the rotors, and they want to all add up to 0. If you, say, fix one of the rotors, so let's fix the outer rotor. Let's make it a stationary housing so that way just this input rotor and the middle rotor want to spin. Then what you do is you zero out omega 3 and you move around this equation and you get yourself a gear ratio. The ratio of omega 1 and omega 2 relates to the ratio of P1 and Q2. I'll show you here. Here's two examples where you're fixing one rotor and the gear ratio that you get in the same arrangement. So it seems like a pretty clever idea that Mr. Tulla came up with out of the UK. Here's kind of a different visualization of it. We're looking now down at like an axial version of this gear. And what I'm going to do is show you these two arrangements. One of them, the one in the middle here, the modulators are fixed. and then the one over here on the right, the outer rotor would be fixed. If you overlay the modulators, then what you start to see is these thick patterns of red magnet and blue magnet actually start to move together, and I'll make it easier for you by highlighting them. So you can see is the inner rotor, which has 3 pole pairs, when it's looking through the modulators, actually starts to see lumps of 3 pole pairs as well. That's how you make the flux look like each other. So it's the secret of flux modulation. So here's a picture of kind of a simulated like flux evolution, and one of our first prototypes that I built when I was in graduate school. But let's talk about our gear and our product. The reason it still wasn't enough for NASA is because after a massive spike in interest across the globe for this technology, right after this publishing of this paper, people tried to build prototypes left and right, and still no matter what, they could not get the torque per unit weight, torque per unit volume, and therefore the cost, they could not get them to compete with mechanical gears. So it still really had a lot of trouble taking off. But there was so much hope in it, right? It was such a neat idea that you could potentially have this series elastic gear, you could potentially have this lubrication-free, contactless, ultra-reliable, super robust gear. And NASA was actually working on it, and they were thinking about it for applications like Robonaut as well as others. So they got all the stops out. They did every advanced magnetic technology you could. They even sliced the magnets to be lamination thin. They used carbon fiber and materials that I can't name, and the thing still blew up and it broke. They tried to make it like so tight and have such tight, small air gaps to get all the best flux transmission. It still didn't work. So they got frustrated, and after the 4th prototype and pouring a lot of money into this, they put out an RFP. And this space cadet right here is the one that answered it. That is me with Mr. Robonaut. So they said that they wanted magnetic gears for space, and they wanted an 1,000-to-1 gear ratio, which is stupid. And they needed it to compete with space-relevant gears. We did it. It was sick. It was awesome. We looked in nature for the inspiration on how this gear might work. So that's like Shaq or like a cat. I'm just joking. That is not what inspired me to make this gear. No, it's a cycloid. Has anyone here heard of a cycloidal mechanical gear?
Rotary engine.
Yeah, exactly. Yeah, it is just inspired by the mechanical cycloidal gear. It is just a magnetic cycloidal gear. And the advantage of this is you get a massive gear ratio, and we're still modulating the flux just like Kaisatala was, but instead we're just making the air gap literally bigger and literally smaller, as opposed to some fancy steel tricks, right? I love the cycloid. I could go into the hypocycloid all day. I won't PhD all over you, but I will give you a fun fact. The Steelers logo is a cycloid. How sick is that? You know? And this is a mechanical hypocycloid, and then this is kind of our first prototype shown arranged there. We had multiple segments, so that way everything would balance out, and that was the first prototype that we built. Our very first prototypes, and I'm a dumb old electrical engineer, I am not a mechanical engineer, so my thing was big, stupid, bulky, and heavy, and we actually competed with Nabtesco cycloidal gears. We were about the similar torque per unit weight and about similar gear ratio in a single stage as them, and that's when we sucked. We have done a lot of development since then, but I'll show just a quick video of kind of the clutching that people get excited about. So you can see the magnet right here is touching that magnet right there, and I'm loading it off screen with a locked rotor, and you'll watch this overload clutching right there. And it's gonna do it again in just a little bit so we can watch it, right? And we're gonna get even more into the math of how that works, but what I'm doing is I'm locking the input high-speed rotor, where you'd have like a motor or a servo, and then on the back side of it, I thought about like going to the gym and paying some like undergraduate $20 to do it, but instead I'm just like hanging from this torque wrench to try and torque this thing at 300 Newton meters. Oh, is it gonna do it again? I think the video stopped. Oh, there it is. We're gonna load it again, and right when that little shim lines up with the base of this magnet right here is when it overloads and it just clutches again. So the relationship between the torque and that loading angle is a perfect sinusoid. That's what got people pretty zazzed. There's no deadband area of backlash. There's no nonlinearity. It is a predictable sinusoid. So here's an example, 25-to-1 4-inch diameter gear, about 50 2 Newton meters for this one here. And the stiffness relationship is just the derivative of the torque angle curve. So you have a cosinusoidal predictable stiffness. Oftentimes, if you are thinking of an application for where you want to use a magnetic gear, do not base it based off of like the peak torque that your old mechanical gear needed, because they needed to maybe survive that shock loading event is why they rated it way up super high. Oh, that's my reminder to shut up. They probably rated it super high for that application so that way they survive these shock loads. Think instead, what do you actually need to do to fulfill the mission or task that you're needing to do, because we protect ourselves in the event of an overload. So a lot of times people base like their mission spec right around kind of 20-30% of what the peak load is. So the model of a gearbox is pretty easy. It's just 2 pieces of inertia connected by 2 ideal gearboxes and a little series spring right there. So if you are a controls guy, you can do a pretty easy controls derivation to figure out how to make some pretty smart, stable controllers for this guy. So we're still working with NASA, and the application that they're particularly zazzed about in the future is this dexterous manipulator, because being a series elastic actuator, we are modelable, controllable, and therefore you can do lots of crazy stuff. Not just touch the object gently and manipulate it gently, but we've already proven that you can do stiffer than passive controls, artificial back drivability, intrinsic safety. So this was this first NASA application, and yes, that got us started. But NASA is not a great customer. They only need a few lunar rovers and a few lunar robots. So when we started a company based off of this technology, we started looking around in industry and asking, where else could this technology be used? There's probably some applications that y'all are thinking of already, but some that surprised us. In about a month and a half, our first gear will be installed at Bluebell Creameries. So even just servo actuators in pretty harsh and extreme conditions like ice cream. Turns out when you're shock loading it with hot and cold over and over, and you have an application that's going back and forth a lot, like pushing together 2 cookies and a piece of cream in order to make those delicious ice cream sandwiches, turns out that that's pretty harsh on the gears as well. And last year they had 5 of 49 of their gears fail. Every time a gear fails, they lose $118,000 in sandwiches not made. So it's a no-brainer to go from a $5,000 gear to like a $10,000 gear, right? When you're looking at these robot applications, yes, our gear is more expensive, but when you're dumping the force torque sensor, suddenly we're pretty competitive again for some of these applications. So we don't just make small gears, we've made big gears in the past, but right now as a company, we're stopping at about 24 inches is about the biggest we're comfortable doing. We're up in Conroe. We've got 9,000 square feet of manufacturing, and I'll just jazz finger you if I talk about like, how great we are. I would love it if you actually talk to our team. They're the ones that really have made our gears more affordable and really understand our customers even more and what they're looking for. This is kind of an example of what we're getting ready to launch this year, where we've done a lot of work to catalogize these gears. So our website will be updated soon with a catalog of just, 4 sizes is what we locked in on. 4 sizes and standard gear ratios that match pretty standard robotic frame sizes. And we can offer it with integrated torque and position sensing capabilities. That's just kind of an example of a few of those sizes. Here's some other things that we're working on. This is kind of a 3D printed just demonstrator of using the torque feedback control to screw in a bolt. This is just like a rapid prototyping application. And the reason this one was a rapid prototyping 3D application was because this particular use case was looking for changing the heads out as well. This is something that NASA is really interested in because they can't afford to bring up multiple robots for different capabilities. They want to have really modular parts to be able to change out, say like the end effector and things like that. So one new area that we're also starting to explore is, since you can just pull apart the 2 rotors pretty easily in our gears, here's a demonstration of a robot actually doing that. You can say have one tool head on, maybe a Phillips or something like that, and what if you could just pop it off and change the gear ratio and pop in another one, and the gear self-aligns, right? We're very forgiving of a little bit of tolerancing. You don't need some super precise harmonic drive style alignment. So The nearest term application, if you go to our website, you'll see we have a launch coming up, and we're trying to show a few things, that is not a ray gun. Actually, that is a real tool that cost $150,000 that NASA used to buy to hand astronauts to repair things like the Hubble telescope. It's a pretty cool little screwdriver. You basically set the torque that you want to bolt the torque to, maybe 10 foot-pounds, and you set it, and then astronauts like just squeeze it, and then it bolts it to that torque. So it's got an intrinsic torque transducer, clutch, etc. They want to put those on the end of a robot and handle those extreme lunar environments, and that's the application that we're working on with NASA. And it's been fun to continue to work with them. We've visited them. If you're wondering where your taxpayer dollars go, it's not just those $1.5 million spacewalks. They plate all their gears in gold. That's actually because of their thermal properties, not just because, but it does look cool. But yeah, that's where your taxpayer money has gone. It's their gearbox there. We've got our first launch coming up during Q&A. I'd love to talk about that. I'm pretty sure we're coming up on the time though. And if you like what we're doing, we invite you to join us. I love that students came. We'll be probably hiring later in the year. It's a startup. It's pretty high risk, but just would continue to love to have a relationship. So that's my last slide. Thanks for the time and attention. I hope that you learned something, and we'll be around for questions.